So as promised, this is example 3 here, and this one is a little bit different. Okay, if you're looking at the original function here, we've got x times the square root of 2 minus x. So unlike most of the examples that were given, this is not a rational function. So we're going to have to draw back on some of the skills that we learned back in advanced functions to think about how this thing behaves. The other thing that's a little bit tricky about this one is we have to go to a little bit more work to figure out what the domain of the function is. Most of the examples where we're working with rational functions, the domain is going to be x is an element of all real numbers, and the only restrictions are going to be the points where it doesn't exist, which end up being the vertical asymptotes. Not so in this case. So let's think, what is the domain of this function? I'll start us off by saying that x is an element of all real numbers. Because x is an element of all real numbers for every question that you're going to see in this course. What restrictions are there on the values of x? Mr. Brown. How did you get x cannot be greater than 2? Yeah, you cannot take the square root of a negative number, so that argument under the square root has to be greater than or equal to 0. And if we do a little rearranging here, we get that x must be less than or equal to 2. Whoops. And I wrote 0, but I said 2. So there we go. So x has got to be less than or equal to 2. This is going to become important later. Let's talk about intercepts. Okay. X-intercept. Oh, sorry, let's do y-intercept first. Set x equal to 0. What do we get when we set x equal to 0? Luca? Yeah, y equals 0. So we've got a nice point, 0, 0. Okay. What about our x-intercept? We will set y equal to 0. And then we will try to solve here. Okay. So let's just write this out. Whoops. I meant to put a square root symbol there. Square root of 2 minus x. How can we solve this guy? Equals 0. What do we think here? Omar. We could, we don't need to factor. We could factor, though. Could we? Yeah, I don't know. And if I don't know, it's probably too hard to factor. There's an easier way. Because it's kind of already factored. I mean, we've got something times something else. So when it's factored like that, what do we do to solve where this thing is going to be equal to 0 here? What do we need to do? I'm avoiding asking Luca because he's answering all the questions. And his arm is getting tired. Arm, what do you think? Don't have to do that. Nope, I'm out here. Yeah, take our two terms, set them equal to 0. X equals 0. Take this thing, 2 minus x equals 0. And then we can solve this thing for x. So here I can square both sides. 2 minus x equals 0. What does x have to equal? X has got to equal 2. Now, when we've gotten these two x values, we need to check something. Right at the very beginning, we figured out our domain, and our domain had a restriction on it. Now, every time we get an x value, we need to check and see if that x value is part of our domain. So, are these things in our domain? X must be less than or equal to 2. Well, this one certainly works, x equals 0. X equals 2 is right at the very end of our domain. So these are both valid x values. Okay, so we've got two x-intercepts. I'm just going to write them as points over here. 0, 0, and 2, 0. Okay. asymptotes. Do we have any vertical asymptotes? Well, how do you find a vertical asymptote if it's a rational function? Okay. Denominator equals 0. We don't have a denominator here, so the denominator can't be equal to 0. I mean, we could imagine the denominator is 1, and 1 is never equal to 0. So in this case, we have no vertical asymptotes. Okay. Horizontal asymptotes. When you don't have a rational function, this thinking about it in terms of horizontal asymptotes and vertical asymptotes doesn't make a lot of sense. So let's instead just think about it like what the horizontal asymptote tells you is what your function does as you go to positive infinity or negative infinity. So let's just think about what's going to happen to our function as we go to very, very large or very, very small values of x. And you did this in advanced functions. You called it examining the end behavior of the function. So let's look at our end behavior here. Imagine taking the limit as x goes to positive infinity of our function here. Say that again, Luca. Yeah, we can't take the limit as x goes to infinity because our domain ends at x equals 2. So there's no point in considering this. So I don't even know what we can say here. Let's say limited by domain. Okay. So we don't even have to consider the end behavior for positive x values because it never goes anywhere. Let's think about what happens if we take the limit as x goes to negative infinity of this function. Okay. And in a case like this, it's useful to think of this, of what happens to each of our factors independently. Think of what happens if we take the limit as x goes to negative infinity of just x, and the limit as x goes to negative infinity of root 2 minus x. Okay? What's going to happen to x as x goes to negative infinity? Avery. It's going to head to something really, really big and negative. Yeah, this is going to go to negative infinity. Now, what's going to happen over here to this second term as I make x go towards negative infinity? So imagine making x really, really big and negative right here and popping it in for x. What's going to happen here, Lee? It's going to go towards positive infinity. So we're going to have positive infinity, and then we're going to take the square root of it. Square root of positive infinity is still positive infinity. So we've got two terms. One goes to negative infinity, one goes to positive infinity, and we multiply them together. Negative infinity times positive infinity is going to be something infinity, but what's the sign going to be? Negative infinity. So this whole thing is going to tend towards negative infinity. Okay? So that's the end behavior. As we go to large negative numbers, this is just going to head off down towards the bottom of our graph. All right, let's take a look at our table of increase, decrease, and our local maxima and minima. So we're going to set our first derivative equal to 0. Look for places where our first derivative does not exist. Our first derivative, if you remember, is 4 minus 3x over 2 times the root of 2 minus x. So when we get to our first derivative, now we've got a rational function. So there could be some weird things going on here. If we're looking for where y primed equals 0, remember we're just looking for where the numerator equals 0. This is pretty easy to solve. We get x equals 4/3 for our one critical point, for one of our critical points. Where does y prime not exist? Luca. Yeah. Basically, if, I mean, you can imagine sticking in the whole thing where this, if this root, let's say 2 minus x, that thing under the root sign is greater than 0, this whole thing is going to not exist. But in our domain, we've already said that anything that is, let's see, x, sorry, not x less than 0, x greater than 2. Right? So basically x greater than 2 here. No, wait. Sorry, this is, should have been the other way around here. It's not going to exist if the argument under the square root is less than 0, which tells us that it's not going to exist anywhere where x is greater than 2, but none of these x values are in our domain. So we're safe. So we have one critical point, x equals 4/3. Set up our interval table. From negative infinity to 4/3, and then from 4/3 to 2, because that's where our domain stopped. Let's check the sign of each of these terms. 2 minus x to the 1/2 to figure out whether our function is increasing or decreasing. Okay. 4 minus 3x is going to go from positive to negative. 2 times 2 minus x square root is going to be positive no matter what we do, because anytime we're taking a square root, we're going to end up with a positive answer. So this thing goes from positive to negative. So our function goes from increasing to decreasing. So we have a local max at 4/3. We do some calculator work, plug this back into our original function, 1.088. Okay. What I'll often do with my local maxima and minima is I'll just take these fractions and I'll turn them into decimals. So I'll take the 4/3 and I'll say that this is really 1.33. And the 3 repeats forever. Just because I find it easier to put the point on my graph that way, rather than trying to visualize where 4/3 falls. Okay. All right, so we got one local max. Next up, concavity, points of inflection. Okay. Second derivative equals to 0. Second derivative doesn't exist. Are our two places. So let's see. For second derivative equals 0, we're looking for, well, let's set our second derivative equals to 0 here. 3x minus 8 all over 4. 2 minus x to 3 over 2. Again, we're interested in just where the numerator equals 0. This thing we can solve pretty easily to get 8 over 3. What is 8 divided by 3? Who's got a calculator? Yeah, thanks. Sorry, x equals 8 over 3. What is 8 over 3? When we punch this in. Mike. Okay. Do we put this point in our critical table, in our concavity table? Of course we do. It's a critical number, is it not? We got to put it in our table. We've got to. Brenda's shaking his head. Why is he shaking? Mike, why don't we put it in our table? Not in our domain. Yeah, our domain ends at 2. So this is not in our domain. Okay. Where does our second derivative not exist? Well, it doesn't exist where our denominator is going to equal 0. So basically where 2 minus x 3 over 2 equals 0. Okay. This is not going to exist, again, wherever x is greater than 2. Okay. So once again, these points are not in our domain. Okay, now wait, that's only sort of true. Because it's also not going to exist where it's equal to 2. Is this a problem? You're thinking, I don't know. Why don't you tell us, sir? You're teaching the lesson. Do you guys think it's a problem? Possibly. You're dying to know the answer, I know. Potentially this would be a problem, but I don't think it will be because we already know that x equals 2 is a special point. It's right at the very end of our domain. So we shouldn't be all that worried that it's possible that our second derivative doesn't exist at that point, because we know that our function kind of ends at that point and weird things are going on anyways. Okay? So we have already sort of, as we've gone through this question, flagged x equals 2 as sort of a weird thing. So I think we can kind of ignore the weird things that are going on there. Okay? That's not really a mathematically sound argument. If it's on the test, this is what I would get you to do, is just sort of say that it's not in the domain. I wouldn't put it in your like, we're worried about points like this because what we want to do is set up the concavity table. So we're looking for these critical points. If I tried to put the point x equals 2 in my concavity table, I would use it to define like the separation between two intervals. It can't separate two intervals in my concavity table because the domain ends there. So there's no interval on the other side of it. Okay? So even if this is a critical point in my concavity table, there's no interval on the right-hand side of it. So really, we can kind of ignore it. Is that better? Okay. So we only have one interval. This is not in our domain. There's no other sort of critical number that we can consider. So all we have to think about is, over our entire domain, is our function concave up or concave down? So these are our two terms. I can imagine plugging in x equals 0 here, and I'm going to get something negative, something positive. So my second derivative is always going to be negative, which means my function is always going to be concave down, no matter what I do. So let's put all this together and finally sketch our graph. We know that our domain ends right here at 2. Okay? And we know that that point, 0, 2, was one of our intercepts. We had an x-intercept at, 2, 0. And we had another x-intercept here at 0, 0, which was also our y-intercept. Okay? We had no asymptotes, but we looked at the end behavior as x went to negative infinity, and we said that our function has got to end up going off to negative infinity as x goes to negative infinity. So it's got to do something way down there like that. We had a single maximum point at 1.33, 1.088. So somewhere in here, we've got that local maximum point. Okay. We knew that our function started off increasing and then ended up decreasing over here. So this makes perfect sense that this thing is just going to go like that. And we can double check with our concavity information. Our concavity said that this thing had to be concave down everywhere, which in fact it is. Okay? And there's our graph. Lee is thinking, yeah, of course that's our graph, duh. But there we go. All right, so just something that's a little bit different because of that restricted domain.